Hey kiddos, happy January, happy 2021. Today we're going to find areas of regions. So if you remember anything about what we did before break, I hope you remember that an area and integrals go together. So these are going to be the same kind of idea. Let me just start with this, an example. So for example, here's what we were doing before break. We had a squiggle wiggle. We called it f of x. And we were finding area underneath the curve from curve to axis by taking areas of rectangles and adding them up. And we were adding them with these infinite sums called integrals. The heights of our rectangles were f of x. The bases of our rectangles were these things called dx. And they were infinitesimally small, so we called this a dx, a delta x, a triangle x, whatever you like. And we'd start at A and stop at B. So the same premise is going to apply today, but what if I throw another squiggle wiggle in the mix? So I'm going to throw a squiggle wiggle down here and call it g of x. So now the area I'm trying to find is the area that's in between these two curves. So I don't want just f of x. I would have a new height to consider. And the new height of this function would be f minus g. Top minus bottom is going to find this height of all of these rectangles in here. So that's what we're doing today. And then I'm going to show you how to type an integral on your calculator. So here's our first question. We're going to do two questions. You have this curve and you have this curve. Now I will start with a disclaimer that I have never seen the AP test ask you to graph really intricate curves without a calculator. So would they ask you to graph these two curves? Maybe, but even then, probably not. But hi, I'm not the AP test, so I'm going to ask you to graph it. Let's start with 2x squared. Are you going to have to graph it on my test? No. And really all you need is a sketch. So here's 2x squared. And the other one, this thing, I know it's upside down because it's negative. It's also a quadratic. And then I think all I really need to know is I'm going to pull. Actually, I'll do this a different way. You're going to like this better. We need to know where these two things intersect so that we can set bounds for our area. So let's just do it that way. We're going to find where they intersect by setting them equal. So I need negative 3x squared plus 10x to equal 2x squared. So I got a polynomial to solve. Let me add 3x squared to both sides. Let me subtract 10x from both sides because I'm trying to make it equal 0. That's how you solve quadratics, is you make them equal 0. So I have 0 equals 5x squared minus 10x. I'm going to factor out a 5x. I'm left with x minus 2. And now I know that these things intersect at 0 and at 2. And honestly, that's all I need. So if I know they hit at 0 and at 2, let me move this over just a little. So it hits at 0. So I'm going to put 0 here. I'm going to put 2 here because who cares? I'm in charge. I know it's an upside down parabola. Do I know exactly what it looks like? Yeah, if I spent more time, but I don't want to. I got other things to do. So that looks like an upside down parabola to me. The end. All right, so the area that we are trying to calculate then is the area that lies between these two curves. So all of this area in here. Let me go ahead and name this upper curve to be y equals negative 3x squared plus 10x. So we're going to find area the same way we've always found area. We're going to find areas of rectangles and add them up. So here is an example rectangle. I know it's a line, but it's a rectangle. It's got a thickness of dx, and it has a height of top curve minus bottom curve. Top minus bottom is going to find the height. Dx is the width of those rectangles. I'm going to start calculating areas of rectangles when x equals 0, and I'm going to stop here when they intersect at x equals 2. And it's 2, 8. I might as well. So they start here at 0, 0, and they stop there at 2, 8. Awesome. That's the setup for your area. The rest of this is, fingers crossed, some old news. Because now I'm going to actually go take the area. I'm going to take the integral. So if I combine my like terms before I start, then all I have to do is undo power rule on this question. So let me add 1, divide by the new. Let me add 1, divide by the new, from 0 to 2. Calculate or evaluate at your bounds by plugging in top and then plugging in bottom. But the bottom's going to make everything 0, so I'm not gonna. This is a cube. So now I have negative 40 thirds plus 5 times 4 is 20. So that would be 60 thirds minus 40 thirds is 20 thirds. All right, here is something that's going to happen now. You're finding areas of regions. So I could take, watch me do it. I could take this whole thing and I could move it and put it in wherever I feel like. Let me put it in the 4th quadrant. So it's the exact same shape. It's just moved down to the 4th quadrant. Its area would still be positive. You're not doing integral functions anymore. You're finding areas of shapes. So like in geometry, you can't have a negative area in this unit. So if you get a negative value, it's probably your bounds or it might be an integral mistake. Okay, the other thing I want to show you today is how to take an integral on your calculator. So step 1, turn on. I'm going to do this in my y equals so that I can show you a really fast way if you have to do, I don't know, 2 or 3 or 4 or 5 of these in a delta math here in a minute. So my first curve, I'm going to type in negative 3x squared plus 10x. My second curve is 2x squared. I could graph it on here if I wanted to, just to make sure my shape looks good. I could graph it on here and check my bounds. I'm sure my window's ridiculous, so I don't care right now. But I could check my bounds to make sure my intersections are happening where I think they're happening. I could do that from table. So look, at x equals 0, they both have y's of 0. And at x equals 2, they both have y's of 8. So those are my 2 intersection points. Your intersections might not be pretty, so you can find them different ways. But what I want to show you is when you go home and we go take an integral. Integrals live here above 7, so I second 7. Because I already have them typed in y1 and y2, I'm not going to retype my functions. I'm just going to do y1 of x minus y2 of x. Then I say I'm integrating with respect to x, and then I put my bounds. Close and enter. And I get 20 thirds. Good thing. So if you're doing 2 or 3 or 4 or 5 of these on delta, all you need to do is go into your y equals, change your functions, make sure your top function is y1 and your bottom function is y2. And then when you go home, all you have to do is adjust your bounds, and then you're pressing enter again. And that can maybe speed this up a little bit for you. All right, we're going to do one more. Here are our 2 curves this time. Y equals natural log of x, and y equals 2/3 x minus 2. Again, I've never seen AP ask you to graph anything complicated, but I don't think these are complicated, so hopefully you don't either. So we're going to have natural log. Let me do them in different colors. Here's natural log in red. The natural log of 1 is 0, so I'm going to put that there. And then this line starts down at negative 1, negative 2, and has a slope of 2/3, so it looks like this. And I'm going to continue this natural log just until they intersect. It's not the best natural log I've ever drawn, but make fun of me if you want. I'll never know. Okay, we're not actually going to calculate the area this time. We're going to set this one up in 2 different ways. We're going to set up for this question an integral that is written with respect to x. And we're going to set up an integral that is with respect to y, because you can write these things some of them you can write 2 different ways. So let's do the x one first, because that's what we just did. I would have top minus bottom. So top is my red curve, which is natural log of x. bottom is the line, which is 2/3 x minus 2 dx. Then here's the work. I'd have to go find these intersections. So these two things are going to intersect here and here. I'm not sure I can do that. Good thing I have a calculator. So in my calculator, you can put them in Y1 and Y2 and look at your graphing screen and go find intersections from your graphing screen. But I would like to remind you of this really super fun solve command. So I go to S, I go to catalog is where I went first. And I'm going to solve, and I'm going to type in the natural log of x needs to equal 2/3 x minus 2, and I'm solving for x. And hopefully it gives me two answers. I kind of think I know where my answers live because I think I have one here, something less than 1 when x is less than 1. Oh, good, that must be that one. So my bounds here are, oops, well, I can't keep it on the screen at the same time, 0.150. You always round to 3 decimal places in calculus and on delta. My upper bound is 5.578. So that's where these two intersection points happen there. The other way we can write this one is we can write everything with respect to x, which means the rectangles that we're making fell down. They're sideways. So instead of calculating areas of rectangles reading from left to right, we're going to calculate areas of rectangles reading from bottom to top. Why do you want to do that? Sometimes the integral that gets set up is easier. Sometimes you have to. So let me show you this guy real fast. This curve, this region, not this curve, but the region that's made here cannot be calculated with an integral reading from right to left or from top to bottom, because if I start cutting rectangles that direction, sideways rectangles, we're fine here, we're fine here, we're fine here, we're fine here. But if I calculate all the way up to the top, this rectangle right here is a curve minus itself, and that doesn't make sense. So you can only do this if you have two curves that when you draw all of your rectangles left to right, you're doing curve minus curve, not curve minus itself. I hope that made sense. I'll say it in class too. So for this one, what we're going to have set up this time, if we're doing it with respect to y, our integral is going to have a dy on it. And all that does is it means everything that we put in that integral has to be y values, not x values. So I need to come up here and I need to solve this thing for x. So I'm going to raise it both base e. Now I have e to the y equals x, and that is now this curve. So x equals e to the y. I'll do the same thing here by adding 2 to both sides, equals 2/3 x, and multiply both sides by 3/2. So I'm just going to write it as 3/2 y plus 2. No, I hate it. I'm going to write it different. This is 3/2 y plus 3 if I distribute it in. Okay, so now when I'm writing the heights of my rectangle, remembering that they fell down, instead of doing top minus bottom, I do right curve minus left curve. So my right curve is 3/2 y plus 3. My left curve is e to the y. Notice that all my variables are y. And now I also have to find new y value bounds because we're reading everything bottom to top. So I need to know where to start, bottom to top. And I'll do that back, in my calculator. So I'm going to have another solve command, and I'm going to have to go solve a new equation. So 3/2. It really doesn't matter what letter you use because you're going to tell your calculator. So I'll use y just because it's there. Plus 3 needs to equal my other curve, which is e to the y. And I'm solving this for y. And I will wait very patiently. Again, I think I know what my answers are going to be. I better have one that's a negative y value, and I better have one that's a positive y value. If I don't, then my drawing is ridiculous or I've solved something wrong. All right, that's what they say. So my bottom bound is negative 1.90, 1.900, and my upper bound is 1.719. 1.719. And if they asked me to calculate that area, I could do it. I'd use a calculator, but I could do it. Let me scoot this dy over so you remember it there. All right, kiddos, that was a long one. Welcome back. Let me know if you need anything.